everybody. Good morning. Thank you for joining this session. And a few words about me. I'm ANDREA IACONO. I'm a software engineer. It's now more than 25 years that I work as a software engineer, and I still love this job. I currently work at Assembly AI, which is an artificial intelligence startup. And my main interest is in data structures and algorithms and artificial intelligence. So today we're going to talk about probabilistic data structures, and we are going to see three main classes of problems: membership, cardinality, and frequency. We'll see in total five probabilistic data structures. And what are probabilistic data structures? Basically, unlike the, let's say, normal data structures we used to work with, they return approximate values. So, for example, if we expect a number in return from a data structure, it will maybe gives us another number close to it, not much close, higher, lower. It depends, of course, of the cases. If we expect a Boolean value, for example, it might return a wrong value, so a false positive in some cases. And we're going to see that in detail in a few minutes. What they do give us, in turn, they allow us to save a lot of memory, and which is the main reason why we use probabilistic data structures. So let's start with the first class of problems, membership. What is membership? Is checking if an item belongs to a set. So as I was mentioned before, in this case, from this class of data structures, we expect a Boolean value. An item is belonging or not. And when do we need to use these kind of tools? In general, when a wrong answer does not involve the correctness of the whole business logic, but just more work. So let's take some example. A taken username. If we want to check if the username is already taken, we can use a probabilistic data structure that can give us a false value, a false result. So let's say we're asking, is this user already registered? Then the data structure will tell us, yes, it is, but actually it's not. So it's a false positive. Then what we are going to do is that we have a query to the database, and we actually realize that the user is not present. So what we have at most is an extra query, but all the times that the probabilistic data structure gives us the correct result, then we have saved time, because database query in the taken username example takes time. And we have also some other example, but let's see how these data structures work. So for the membership, we're going to see three data structures, and we start with the Bloom filter. So a Bloom filter consists of a bit array of size m and k different hash functions. The membership condition, so what we're going to do in order to implement the filter is to check if all the bits that are set, if all the bits related to an item are set. And that is the condition we're going to check. Let's see this in detail. So in this example, we see a bit array of size 16, so m is 16, and we use three hashing function, so k equals to 3. Let's start for the in this slide. We have the first item we insert is x. So we apply the first hash function to x, and we get a number in result. And in this case, for x, the first hash function returns 1, which is the second item in the array. And so we put a 1 in the array there. Then we apply the second hash function, and we get 3, which is the fourth element of the array. And then we put a 1 in that location. And the same goes for the third one. So after we apply the hash functions to x, we have the initial array, which has 3 bits set to 1. And then we insert y. We apply the hash functions to y, and we apply the first one, and it gives us 3 again. So there's a collision. in this case, since the bit is already set, we leave the bit set. And then we apply the second function, and we put a 1 into that location, and again for the third. And the same goes for when we insert z. So we insert the other 3 bits, and also in the third case with z, we have a collision. And how do we check? So we take the same bit set. As you can see in the image, the bit set was already set with x, y, and z, and we check for the item e. So if we check e, we see that we apply the hash function to e, and we get 3 different results. And we check the bits at those locations. In this case, the first hash function applied to e gives us a value of 1, so the second location in the array. We check the bit is set, okay. Then we check the second bit and is set. The third bit is not set, because as you can see, the third one points to a 0. So in this case, the condition is not met, because the condition was to have all the bits set. And in this case, this is not true, because only 2 or 3 are set. So in this case, the Bloom filter will tell us that the element e is not part of the set. So it's a negative, and it's a true negative, because we inserted only x, y, and z. So it's true that e is not part of the set. Then we check y. Y is one of the elements that we set, and we check if all the hash functions, all the indexes mapped by the hash functions are set to 1. And this is true, because it's if we check the positions there, we see that they all map to a 1 value, meaning that they are all set, the condition is met, and so the Bloom filter will return true, because it thinks that y belongs to the set. And now let's get to the tricky part. Let's say that we have an element g, which the hash functions map to elements in the array which are all set. In this case, the Bloom filter will think that g is part of the set, even though actually it's not, because in this set we only inserted x, y, and z. So in this case, the Bloom filter will give us a false positive. It will tell us, hey, this g element is part of the set, while in reality it was not, because we didn't insert it. So how do we deal with these errors? So they're not errors, but because we know that it can fail, but how would we deal with that? We can approximate optimal size for the bit set and the number cake function in order to meet our needs. So given a value n, which is the numbers of the items that we expect to insert in the set, and given a rate epsilon, which is the false positive rate that we want to allow, then we have this formula in which we compute m and k based on these values, and we can have the optimal values for our Bloom filter. So in this example, in the lighter gray box here, if we want to check 1 million items with 1% error rate, then the number of bits of the bit size will be 9.5 million, which is 1.2 megabytes in memory size. And the number of function k is 6.6, so it's 7. And in this way, we know that we can check 1 million items, that the error rate will be 1%, so only one, on average, only one request of membership will be, only 1 in 100 will be false. And this in 1.2 megabytes of memory. And this size is not going to change, whatever the number of the elements we put into it, and how many times we do that. In this graph, you can see that, as you might expect, going to the left, the curve of, on the y-axis, we have the number of bits of the bit array, and on the x-axis, we have the false positive rate, epsilon. So the more we want the Bloom filter to be precise, the more memory we have to put into it. And that's quite obvious, I would say. But the nice thing to look at is how steep the curve is. So if we want to allow 10%, it's quite acceptable. The less error we want, the more the size in bit has to grow. Now a fun fact. The fruit flies already developed this kind of algorithm in millions of years ago. So how do they assess if they are dealing with a new smell that they didn't experience before? They just use their brain evolved a neural circuit that has the same characteristic of a Bloom filter. There's also there's a link to the paper which explains that in detail, and it's quite interesting. And here you can see an implementation of the Bloom filter. As you can see, it's really a few lines of code. This is, of course, not production-ready code, but just to give you an idea how easy it is to implement that. The code is in Kotlin, and there's a function, there's a class hasher at line 12, which has the code function. Since we have to develop multiple hash functions, this is just parameterized. And then there are two methods, contains and add, which will just return if the bit is set or not. And this code is available on GitHub. At the end of the presentation, there's the link of the repository. But what if we want to remove an element? So let's say that the upper bit set is the current state. We want to remove X. So if we set the bit to 1, when we inserted it, we can remove it. So we can set it to 0. But what it happens is that due to the collisions, if we remove 0 from one point, we are going also to interact with other elements. And in this case, we remove X, and then we check Y, and one of the bits removed by X was also used by Y. And so if we're going to check Y afterwards, it's going to say that it's not present, but actually Y is present. So not only we have a false positive, but you also have a false negative. And do we really need a data structure that may give us false positive and false negatives? Of course not, because then we don't know what to do with that. If we want to go, if our use case needs to delete elements, then we can use a counting Bloom filter, which is a very, very simple extension of the Bloom filter that we just saw. Instead of having a bit array, we have a count array. So we use a number instead of a bit. And the rest is the same. So if we insert X, instead of setting a bit to 1, this is a number, so we increase the 0 to 1. And when there's a collision, of course, we increase the number that we found. So when we insert Y, there's a collision at the second hash function, and so the value from 1 becomes 2, and so on. And how do we check if an element belongs to the set? We just check that all the values are greater than 0. And in this case, E maps to 1, 1, and 0. So the counting Bloom filter will say that no, it's not belonging to the set, and that's true. We didn't insert it. We check Y, and we see that the values are 2, 1, and 2. They're all greater than 0. So it's positive, and it will return true, and it's really true because we inserted Y. And this is the case for the false positive. Again, as before, we have G which maps to positions that were set by other elements. And also in this case, it will return a false positive. But what we can do, unlike the Bloom filter, is that we can remove elements. So if we want to remove Y, we just take all the positions that are mapped with the hash function and decrease the value that we have in those positions. And in this way, everything still works. There's a short implementation of the counting Bloom filter, and here there's the only difference is that instead of setting a bit, we increase the value, and there's also a delete function. Oh no, there's also another thing. Since the Kotlin data type of byte, it's a signed byte. It means it also allows negative values, and so you can see at line 4, I just initialize the array with the minimum value, which is minus 127, and then I will check in line 9 that the value is greater than the minimum value of the byte data type. While in the examples I showed 0 and 1, 2. In this case, it will start from lesser values. But there's a drawback in using counter filter. While we were using bits, of course, every single element in the bit array was just 1 bit of size. In this case, if we implement with a byte, it will be a byte, so 8 times more. If we use a short, it will be 16 times more. 16 times more. If we use a int, it will be 32 times more. And it will also might overflow. So, and if you remember the code that I showed before, that didn't check for overflows, for example. So this is not, if we are interested in deleting elements from a set while we're checking for membership, counting Bloom filter probably is not the best solution. So there's another probabilistic that, so there are a lot of others, but in this presentation we will only see another one, which is the Cuckoo filter, which tries to address these problems. So this is based on Cuckoo hashing, and Cuckoo hashing is a classic data structure, so it will return exact values. And the Cuckoo filter is based on that. So to explain how the Cuckoo filter works, we need to understand how the Cuckoo hashing works. And so we're going to see that in detail now. The Cuckoo hashing consists of 2 arrays, which we will call B1 and B2, and 2 hash functions, H1 and H2. So let's say that we want to insert X, and we apply the hash functions to X, and we get a number in result. So the first hash function will return 2, and the second hash function will return 7. Okay, those 2 are the indexes which we have to store the value in the arrays. So in this case, we just choose the first one, which is 2, and we put the value. We write the value in there. So we write value in the first array, so in B1 at that position. But we know that the other position, the alternate location that we might write X in the array B2 is that one that was that is pointed by the arrow, which is at position 7. So the index that the second hash function was giving us. Now we insert Y. We insert Y, we apply the 2 hash functions, and the first one gives us 10, and the second one gives us 0. So those are the 2 locations. They are both empty, so we just write Y in the first array, and we keep track of the position where we might write Y if we use the other hash function. Now we want to insert Z. Here's things become interesting because Z, the first hash function, maps to a location which is already written. It already contains X. The second one, though, it maps to an empty location. So we're just going to write Z in the second array because it's empty. But we keep track that it points to another location on B1. And now we want to insert W. The point is that the 2 hash functions applied to W gives us 2 positions which are already used in the array. So what do we do then? We choose randomly one of the 2 arrays, and we decide to put the value in there. In this case, I randomly chose to write W in array 2. So in the second part, you can see that I wrote W where Z was, and then I kicked out Z. But what do I do with Z? Well, Z now goes to its alternate location. The alternate location was used by X, so Z, it's written there, and it kicks out X. X, we will just move, it will be just moved to the alternate location, and its alternate location is this time an empty position in the set, in the array. And so I'm going to write it there. So this is how Cuckoo hashing works. And its performance are quite nice because it has a constant lookup runtime complexity, because of course I apply the hash functions, and if it's not in the first one, I apply the second function. If it's not in there, well, it's not in the set. So it's a constant time operation. Delete is the same. I just check if it's in the first, I apply the hash function, I go to that index, I see if it's contained. If it's contained, I remove it. Otherwise, I will go to the other one and remove it from there. And that's fine as well. Insert, that's a bit more tricky. So, as we have seen, what happens when we insert something? It can happen that it might kick out other elements for their position and keep doing that. So even though this might be tricky because it can be a cycle, for example, and then, of course, we cannot do anything. Or maybe we can have a threshold which we don't want to go over because it takes too much time. Then in these cases, we need to enlarge the arrays and rehash everything. But despite all the extra operation, the amortized runtime complexity of insertion is still constant. And this is for Cuckoo hashing. So how do we use Cuckoo hashing for Cuckoo filter, which is the probabilistic data structure that we're interested in too? First of all, instead of saving the elements, storing them into the array, we just store a fingerprint of the item, where a fingerprint is just another hash function. So it's a function that allows us to have a fixed size of what we are storing there. So we apply a fingerprint, we store the result of the application of the fingerprint function of the element. And then how can we get the alternate location where to check and eventually to kick out elements when we are doing the insert? We don't have the element anymore. We cannot apply the hash function because the element is not there. The element, what we have in the array is only the fingerprint of the element. So the tricky part is that we use a couple of hash functions that keep tracks of the fingerprint. So as I said, the fingerprint is a function returning a fixed bit size value. And the two hash functions are, the first one is defined as a normal hash function, and the second one is defined as the result of the hash function XOR the hash of the fingerprint. Now, given that in this case we leverage the XOR symmetry property, that allows us to say that we can have the hash function 2 computed based on the result of the hash function 1, and symmetrically we can compute hash function 1 based on hash function 2. And now we're going to see this in detail. So this example as before, we want to store x. And we compute the hash function on x, and we get two values. Then we store the fingerprint of x, not x anymore. Then we are in the case in which we need to kick out the element, right? And how do we know? So since z will be written instead of x, the fingerprint of x, how do we know where to put f of x in the other array. We don't have any x anymore. But as you can see, there are the two hash functions are written on the top left on the slide. The position on the second array is given by h2 of x, which is h2 of x XOR the hash of the fingerprint. So we have the fingerprint because we want to write z there, so we know the value because we can access the array. We apply the hash function to the fingerprint, and then we XOR it to the hash of 1. And the hash of 1 was just if you remember, the hash were used for computing the index. And we know the index of fx. Of course, we know it because we want to write something into there. And so in this way, we get the result of hash function 2. And so we know the location where to write f of x. So the lookup of x, which is exactly what we want from our probabilistic data structure, is that we have to check, we check if the fingerprint is present in the locations that we map in the array. Now, what is the probabilistic part of this stuff? Is that we store fingerprints. Fingerprints are a reduced size, let's say, translation of the item. And so, of course, since it's a reduced size, we might have collisions. So two different elements might have the same fingerprint. And in this case, if we want to check and the lookup says that, hey, the fingerprint is matching, maybe it's not because there's a collision. And in this case, we have a false positive, like in the Bloom filter case. But we know that this can happen, and so we don't worry about that. So this formula tells us what's basically the occupation, and just to make it easy, it's a bit better than Bloom filter, which is a very, very nice result, given that unlike Bloom filter, the Cuckoo filter allows deletion. So if the use case you're interested into needs deletion, then the Cuckoo filter is not only it allows it, but also it has a slightly better performance in terms of memory than the Bloom filter. Here there's a simple implementation of the insert function. So you can see that at line 4, we're checking if the bucket is already taken. If it's not already taken, then we put the value into it. Then we check the second bucket. If it's not taken, we just insert into there. Otherwise, we'll have a for loop at line 16, and there's the maximum number of times in which I try to kick out elements. If there's a loop, this for will reach its maximum times of attempts, and then we'll return false. If the function return false, it means that the two arrays need to be enlarged and rehashed. So this was a brief overview of the membership class of problems. Here there's a list of libraries which implement a lot better than my code these data structures. And let's get now to the second class of problems that we want to see now, which is frequency. So here's a nice SKCD comic about that. And what is frequency? So with frequency in this here we mean counting the number of times that an item appears in a stream. And we're going to see the count means catch data structure for doing this. So we have some frequency use cases like unique users of a service, the top K items. There's a lot of them, but this will be a lot shorter than the other data structure that I showed before, because it's basically a counting Bloom filter multiplied. So we're going to see that in detail. The count means catch data structure consists of D hash functions and a bidimensional array of size D and W, and we can define the D and W, so the size of array, given the error rate and the probability we want to have for our frequency data structure. So in this example, if you want to have an error rate of at most 0.1% with 99.9% certainty, then the size will be around 76 kilobyte in all, using 7 hash functions. Now let's see how it works in detail. This is the initial state. It's a bidimensional array. It's full of 0. The first row is the one that we map with the hash function number 1. The second row is the one that we map with the hash function number 2, and so on. So we want to insert x, and we apply the hash function, the first hash function, to x, and it gives us 2 as a result. So we put it in at index 2 of the first array, and gives us index 13 for the second array, and we put it there, and so on for all the hash functions. Then we insert y, and it goes as before, but the things to note here is that the second hash function has a collision. So it gives the same result as the second hash function applied to x, the element that we inserted before. And in this case, we're going to increment the number. So as I said before, this is sort of counting Bloom filter, just applied to more hash functions. And again, I insert x again, and I increase the values. So how do we get the count? So frequency is for counting how many times we've seen the elements. So the count of x is just the minimum of all the items that we inserted the values for x. So in this case, it's the third element for the first row, it's the 14th element for the second row, and so on. We get all these values, which are for x are 2, 3, 2, and 2, and the minimum of them is 2. So this is the number of times we've seen x in our stream of data. The same goes for y. We count all the elements of y. It's 1, 3, 1, 1. The minimum between these 4 numbers is 1. So 1 is the number of times that we've seen y in this stream of elements. Why it's probabilistic? Because, of course, we're using hash function, and also this time, if there are collisions, we get higher numbers, because maybe there are numbers that maps to the same index of the elements we're checking, but there were not. So we get a number that was not increased by element itself, but other elements. And so in this case, we'll get higher counts. So this is something we have to be aware of when we use this kind of data structure. And here you can find a very, very simple implementation of the count mean sketch code. It's really similar to the counting Bloom filter, because, of course, it's the same idea, the same underlying idea. And we have some libraries that implement it. Here, there's the link for them. And then let's come to the third class of problems, which is cardinality. And cardinality is counting the number of distinct items in a collection. And we're going to see hyperloglog. So there are some use cases. If you use, for example, in BigQuery, you use a prox count distinct. Maybe you don't know, but you're using this kind of data structure to get the result. And there's also a lot of other use cases. But let's see, let's start with an idea to understand how hyperloglog works. And the idea is, let's imagine we have a set of random numbers, completely random numbers. Now imagine their binary representation. You can, I think, safely say that roughly half of them, their binary representation will start with 0, and the other half will start with 1. I think it's a legit assumption. But also we can say that around 1/4 of them will start with 0, 0, another fourth with 0, 1, the third fourth with 1, 0, and the last one with 1, 1. That's also legit. And the same goes with 3 bits, 4 bits, and for all the bits those numbers are made of. So there's a general rule here. So the probability to have a specific set of bits as leading bits of a number, that probability is equal to 2 to the minus k. Now, how hyperloglog leverages this thing? So let's imagine we have a big set of items which are hashed to numbers. So we have this big set of random numbers, as we said, as in the example we saw before. And if we add a number to the set which starts with 0, 0, 0, 0, sorry, 4 zeros, then we can say that it's likely that the set has the size of 2 to the fourth. So 4 zeros, 2 to the fourth, so 16. So a couple of caveats here. This works on big cardinalities, and the hash function, this is very important, must return uniformly distributed binary representation. Otherwise, it won't work efficiently. So, hyperloglog data structure consists of a hash function and an array of integers that we call m. So with only one hash function, we risk that one single item can skew the result. So we use multiple hash functions. So for example, let's say that we use only one function and we insert, I don't know, some elements, and then we insert an item which is hashed to a very low value. So I don't know, 2 or 3, just as a number. 2 or 3 as a number has a lot of leading zeros. So that will skew completely the correctness. So we use more hash function so that we don't, if we, even if the element with one hash function, we get a skew result with it, the other ones will somehow mitigate this because we're going to get an average of all the hash functions. So let's say that we have, in this case, 16 hash functions. We apply all of these to the number x, which is to the element x that is the one that we're inserting, and we get numbers. And I'm showing here their binary representations. The first one has 4 leading zeros, and so I put in the first element in the array, I put a 4. The second hash function mapped to a number that has 2 leading zeros, and then I map the second element in the array with 2. And I do it for all the 16 values, and I get this array M. So this is an array with all the values, and then later on I will explain you how I'll get an average to understand which is the average number of leading zero for all these hash functions, which is the one that we're going to use for getting the count. Then I insert y. The first hash function mapped to a number that has no leading zero. From before, we had 4 as the number in the first position in the array. So 0 is lesser, and so we're not going to change it. The second hash function mapped to a number that has is 1 leading zero, and so is lesser than 2, and so we don't do anything with that. The third hash function maps to a number that has 3 leading zeros. The value that we had before was, it's not working anymore. The value that we had before was 1, and now we had 3 because it's greater. So, computing multiple hash function is computationally expensive. So, can we do what we did it before in this example with just one hash function? Actually, we can. We can split the outcome of a single hash function and pretend it is more than one hash function. So, applying the hash function will return us a number, and we have here the binary representation of this number, and we say that we take the first 4 bits and we use those for computing the index in the array when we want to put the value. And then we count the leading zero in the remaining part. The remaining part is these 12 bits, and the leading zero is just 1. So we're going to put in the index given by the 4 bits, we're going to put 1, which is the number of leading 0 in the second part in which we split the number given by the hash function. Let's see it in practice. So we insert x. We apply the hash function, we get a number. This is the binary representation of the number. We take the first 4 bits. The decimal value of 1100 is 12. So 12 is the index where we're going to write the number of leading 0 into the array. Number of the leading 0 is 1. So we're going to write a 1 in the array M at the position 12. In this way, so we have here we have y. Again, we take the first 4 bits. The decimal representation of 0101 is 5. So and the number of leading 0 is 4 in the rest of the bits. So we're going to put a 4 at index 5 in the array. So at the end of the day, we are going to fill up the array M as we had before with 16 as function, but we're using only 1. Oh, here is an example, of course, because if, as before, if the number, in this case 1 leading 0, is lesser than the number that we had before, in this case it's 4 at index 5, then we are not going to update it. But how are we going to compute the cardinality then? So to do that, we use a normalized harmonic mean, which is Z, of the values of the array M. So we computed all those values in the array. We use an harmonic normalized mean, and we apply a correction factor, which is called alpha, which according to the size of the array M has a different value. And we can also compute the error rate given the size of the array. So let's see it in practice. Let's say that the array M at some moment in time has this value. We want to have the cardinality. Remember that we are counting the number of distinct items in the set. So we want to know the number of these distinct items. We're going to compute the the normalized harmonic mean, and we apply the correction factor, and we get a number. So this is the estimated count of elements, of distinct elements in the set. But let's see another example. I highlighted in red a number. So if you see in the first example, the number in that index, at that index is 2, while in the second one it is 12. So it's a lot of difference. Do you remember that we said that we're talking about powers of 2? So if there's a difference of 10 between 2 and 12, we're talking about 2 to the 10th difference, so it's 1,000 times more. But applying the harmonic mean, normalized, and the correction factor, the difference between the two is only less than 30. So in this way, we manage to make sure that the skewed elements do not alter very, very deeply the outcome of the data structure. And this is the strength of the data structure. Here's a very, very short implementation. As before, this is not production code, but it's just to give an idea that with really few lines of code, we can have a working implementation and see how it works in practice. As in the keynote, in the keynotes that we listened to before, practicing, playing with technology, and trying to play with code and coding ourselves is the best way to learn it. So this is a great way if you want to get your hands on with these probabilistic data structures. The best way to do it is just writing some code for doing that. And again, as before, we have libraries that implement all these algorithms and data structures in a better way than I did in this code, but in this slide, sorry. But here's a recap and a takeaway from this presentation. So the huge pro of using probabilistic data structures is that they allow us to save a lot of memory. So there are a lot of situations in which memory is important. If we are working in embedded context, for example, or if we are dealing with a huge amount of data, saving memory is very, very important. The cons, of course, uncertainty. So we need to make sure that if we get a wrong result or an approximate result, let's say, this is not going to screw our business logic. And of course, the cold start. As soon as I showed before, we start inserting data into the Bloom filters, into count, mean, sketch, into the hyperloglog. What if we have to restart our servers? So we can take snapshots, we can have other strategies, but this is a problem. Of course, we have to think about if our use case really can leverage the probabilistic data structures. Also, distributed. Do we live in a distributed environment? Do we need to leverage multiple servers to do that? Distributed cache might be. It depends, again, on your use case. But this is something that you have to take into account if you want to use these probabilistic data structures for being effective. So there are the links of the original papers. And there's also the link to the code that I showed in the presentation. And do you have any questions? So if there are no questions, it's either because I was a great speaker and you perfectly understood everything, or more probably there's a lot of things to digest and maybe things will come out with time. I will be around the whole 3 days of the conference. You can just reach me and ask me whatever you want in these days. Thank you very much.